Hello students, this is chapter number 2 only, and this is the lecture number 5. Okay, so far we looked at 1D element for different kinds of elements. Rather, we looked at started with a spring, then we had heat transfer, right? We had heat transfer, diffusion, then we had electrical, basically resistance network, then looked at poroelastic model, poroelasticity, then fluid flow, etc. Okay, and the not to forget, the very important one was the 1D bar, 1D elasticity, and this is the one which we will talk about today. We will make it a little bit more difficult. Difficult means we will take into account of a few more things that will make it problem more difficult than earlier. Okay. So let's today we will also understand the different meaning of K1, K11, K22 and so on. So let's say this is a bar, elasticity 1D bar. So this is 1D bar. This is node number 1, node number 2 here on the right, on the left side doesn't matter. What we want to find out is what is the value of K. Ke means element stiffness matrix Ke we want to find out. So this is equal to what? We know already that if E is there, E is the Young's modulus, A is the area, L is the length, then we know already this from the previous class that Ke is equal to Ea over L, then you have 1 minus 1 minus 1 1. But we found this from from some equations, and so that give you some one perspective. But if you want to have little more insight, we can also pose the problem like this. So let's say this bar, and you want to find out what is the stiffness matrix. You can also do some experiment in your lab, and how this will be like this. So you take this bar to your lab and write 1, 2 at the two ends, and then what are you going to do? You will fix one end like this, and you will apply unit displacement here. Okay, so this you are going to move by 1. So you will say U1 equal to 1. By moving 1, whatever force you need to do that here will be actually K11, and whatever force you get at the other end will be K12. Yeah. So So if you apply K11 basically meaning will be K11, K12, K21, K22. That's what it is, right? So inside you get from here, what I mean to say is, if in your lab if you want to find out K11, how will you do it? You will take this element and you will fix at 2 and apply, and you move this end by unit displacement u1 equal to 1, and whatever force is needed to move it by 1 will be K11. K12 will be whatever the force needed to balance here. So first let's find out what will be K11, then we can find out K12. Okay. Now we know that sigma equal to E times epsilon, and in this case epsilon will be equal to u1 over L, but u1 is equal to 1, so it will be 1 over L, and sigma is nothing but, in this case sigma is K11 only, right? K11, because this is the force that resulted into displacement equal to 1. So sigma in this scale will be K11 divided by area. So we write K11 divided by area. So rest is what we get from here. We get sigma is equal to E times epsilon, which is 1 over L, equal to E over L, but sigma itself is equal to K11 over A. So we write K11 over A is equal to E over L. That tells us K11 equal to E times A divided by L. So what do we get? We get simply K11 equal to EA over L. So this is what you got. Okay. Next thing is we have to find out K12. You got K11 which is equal to E over L, and here you see EA over L multiplied by 1 equal to EA over L only. What you understood a different meaning, okay, and this we will use basically, yeah. So this understanding we can use. What we are seeing here, we are not, this course is not only about mathematics but also about some physics as well, and especially when you are working with structures and all, physics becomes very important. And with respect to that, what is a stiffness and all, in fact a stiffness name itself comes from the physics only. So if you want to find out K12, what is the meaning? Meaning is, if displacement at node 1 is unit, then whatever force is needed to give this node 1 displacement equal to 1, that force is called K11. 1 for force at 1 and 1 for displacement at 1, right? Rather it should be displacement at 1 and force at 1, sorry. So K11 means give displacement of 1 at node 1 and measure the force at node 1 is K11. K12 is give the displacement unit at node 1 and measure the force at node 2. In order to balance this force, how much force you have to apply here? You have to apply the same force in opposite direction. Meaning that if we had this condition in which you applied what? You had K11 and you had K12. This node 1, node 2, this U1 equal to 1, and you had U2 equal to 0 because it's fixed. And we know K11 we have calculated is equal to EA over L. In order to balance this, you have two forces here. Which all two forces? You have one force K11 which gave unity displacement to node 1, and then you have K12 which will be required to balance this because it is fixed. This end is fixed. Hence, whatever the force, reaction force applied, reaction force to this end will be the one which will be K12. Means unit displacement at node 1 and measure the force at node 2. Okay. Okay. So, if you look at this one and this one, since I have drawn both the arrows in same direction, then we, in order to, for the equilibrium, we get F11, sorry, rather K11 plus K12 equal to 0, and hence K12 equal to minus K11 will be equal to minus EA over L. So, we got like this one. Now, same thing we have to repeat for node 2. We have to find out K22 now. For that, K22 means, so rather let us write here meaning, or instead of Ij. Okay. Displace ith node by unity, and J is measure the force at jth node. So, this is what the meaning we understood, right? Okay. So, let us see in what is K22. So, we have like this, and what we will do now, we have to find K22. That really means we apply unity displacement at node 2 and apply the and measure the force by fixing all others, remember. Okay. So, it is very important. Okay. You write while fixing all other nodes. Which nodes? Where displacements are not applied have to be fixed. Okay. Where, so you are fixing, you are not fixing the one which need to be given unity displacement. So, in this case this is 1 and 2. Since you are going to give unity displacement here, U2 equal to 1, so you are not going to fix it. All other nodes have to be fixed. So, you are fixing node 1. Again, in this case as well, if you want any displacement like this one, the K22 will be the one, the force that you will measure, it will be K22, and we can write like this. So, this is U2 equal to 1, this is K22, and this will be K22 K21 and displacement U1 is equal to 0. K22 you can calculate the way we did earlier, and we will find that if you want displacement of this equal to 1, K22 has to be equal to EA over L. Similar analysis you can do as we did in the previous page. And again K21 plus K22 equal to 0, and hence we will get K21 equal to minus K22 is equal to minus EA over L. And hence we get all the elements we got earlier. We got K11, we got K11, we got K12. Similarly, we got K22 and we got K21, and hence the element stiffness matrix we got is equal to EA over L 1 minus 1 minus 1 1 like this one. Okay. So, this gives you a different meaning. Now you can look at this as forces required for the unit displacement, and it actually makes sense if you see that earlier when you had a spring and then you say what is the spring stiffness, and what you said? You said you apply force. So, you apply displacement u equal to 1, and whatever force is needed to move this by unit is stiffness, right. So, basically F equal to K times U. If U is equal to 1, hence F equal to K, that is what you did. Only difference is now a stiffness term is not a scalar term, a scalar value. It has a this is like a matrix, meaning that we have little bit different meaning of that. We are applying force here and measuring we are applying displacement here, measuring force here, applying displacement here, measuring force here. Similarly, applying displacement here, measuring force here, and applying displacement here and measuring force here. So, that means it has little bit different meaning, but this is what you do in this case of this one. What we have done earlier, this is just an extension of what you do here. What I mean to say is, it is absolutely possible that you have one structural element 1D bar, you take it to lab, you do some kind of analysis the way we did here, and what did we do? We took a bar here and then we fix the node where the displacement is not applied. You apply displacement at one end and you measure what is the force you need to displace it, yeah, and so on. You keep on doing like that. So, basically now why we did that? Because if we understand the meaning of this, we can now work on little bit difficult problem. And what kind of problem? Problem of truss. If you see, the truss has this kind of members, right. So, you will have like this, like this, like this, like this, right. Okay. And then here this could be something like this, yeah. So, what you see here, there is a hinge here, the roller support here, there may be force F goes like this, F1, there is force F2 and so on. If we want to solve this kind of problem, then we have to accordingly think. Whatever we studied so far, we will not be able to apply. Why? If you see if you just a bar, our forces are axial forces only. Yeah, all the forces were along the length only. But now if you see the force is coming in this case perpendicular to this one, to some angle to this one, and so on. That means we have to formulate that way. Okay. All the elements whatever we studied were based on some kind of conservation principle or some kind of law basically. So, if you see in case of electrical network, it was possible to make the we make some star type of network, right. So, we R1, R2, R3. It was possible to do it because current here does not matter whether is current coming from this side or coming from this side. You just add them. This is I1 from this side, I2 from this side, you just add them, this becomes I1 plus I2 and so on, regardless of the direction of the wire, right. See, it's coming from this one, you don't care, you just add them like this one. And so, all those looks like 3D, but actually this is 1D only, meaning that whatever we formulated for 1D element, that it just works there. Why it works? Because all the voltage and currents all are a scalar. We can treat this like a scalar because our resistance is 1D, and if resistance is 1D, what it matters is what is entering, what current is entering here, right, flowing to this one, that is all. Unlike the case when you have a like a bar, something like this one, then it matters whether your force is this way or that way. See, it matters. Things will be different if you load, let us say if you fix like this one, and if you apply a load like this, then this beam will bend like this. If you apply load like this one, it will go like this. Although our formulation is not for bending, but still when we have a touch type of thing, then depending on the direction of the forces, we will have a different kind of stresses inside this member. So, the bar 1D bar behave little bit different from your electrical network, where what is the difference? Difference is the force or displacement, those are vectors. In this case, your currents and voltages, those are scalar quantities. Okay. So, in a way you can say that we need it follows different kind of law, this follows different kind of law. Here you have conservation of charges, but this one is based on the Newton's law, right. Summation of forces will be equal to 0, and force itself is a vector. Force or displacement, these are vector quantity, and hence this if a structure becomes 3D, you have to look for, you have to formulate such a way that force also becomes, if a structure is 2D, you have to make such a way that force becomes 2D or displacement also becomes 2D. If your structure is 3D, then accordingly the force, you have to take force 3D force into account, displacement also 3D into account. In this, it does not matter how you connect, whether you are connecting all of them in line like this one, or you are making like this and like making like this one. Actually, it has the same thing. Yeah. So, what I mean to say is the difference between one electrical circuit like if the electrical circuit is like this one, right, and if you have this is R1 and R2, and if you have a bar which goes like this and this, yeah, okay, both have different meaning. This one will nothing will change. This the first one is similar to this R1 R2. So I. So this the first one and second one both are actually exactly same. There is no difference this and this. Both are exactly same, but a structure, if you see this one, if we have some kind of force here, F, we apply F here, yeah, and let's do like this one, yeah. Okay, so here we can so here I have grounded, here also I have grounded, the same way I have grounded like this one, yeah, and if we draw like this, yeah, both are not the same. You got it? So if we have our circuit like R1, R2 joined like this one, current coming here going like this one, this will be equal to R1 here, R2 here like this. But the same thing if you have like this and same element is this one here, same one is here, but you are aligned and you are applying a force, you will have different kind of stresses, yeah. Especially this one, you see it, in fact it is going to bend, but in this case this is not going to bend, it will take the axial load. In this case there will not be a net axial load, yeah. So hence this and this configuration are not the same, hence formulation of this will be different from this one. This one is based on conservation of charge. So what it matters is how much charge entering here, how much it is leaving here. In this case is not like that. What it matters is the summation of forces in one direction has to be 0, summation of the force in another direction has to be 0. So this is based on Newton's law, this is based on conservation of charge. Similarly, you can have a pipe as well. Let's say you have a pipe here which goes like this one and comes like this, yeah. So as long as it does not matter how it is going like this and this is similar to going like this one and straight goes like this one, unless there is a unless you maintain the same pressure, whatever pressure you have here you give the same pressure here, as long as you give you have that same condition, it will both will be exactly the same, because this is based on conservation of mass. Basically whatever the mass flowing here, it will get out. Similarly this will be like this one level, okay. So basically the Poiseuille equation that we have applied, it will depends on pressure. Pressure is again a, it works like a scalar quantity in this case, okay. And pressure is a scalar basically, if you say the actual pressure is a scalar only. So but here force, since force is involved, hence it will have direction and all, okay. Well, what I mean to say is when we want even like a spring, let us say we have a spring like this. Like this one, yeah, and always is 2D. Let us say so this is k like this. Okay. Now, if this is something like your configuration is something like this one, and you want to if your forces are like this, yeah, either the force can be like this one or this one. Similarly, this can also move this way and that way. Then we have to change the formulation. We are going to work we have to find out the stiffness matrix for this one. Let us say for we have linear spring with a stiffness k, and for this configuration our value we have to find out the stiffness. So, for the stiffness matrix for this one will be k equal to k e is equal to k 1 minus 1 minus 1 1. In this case, for the first case we have to find out, and how will we find out? We have to look at we have node 1, node 2. However, now if you see, the degree of freedom will change. We have 1 here, 1 here, 1 here, 1 here. So, accordingly we have to formulate such a way we should be able to apply the force this way also, that way also, this way also, this way also. That really means that stiffness matrix in this case, like we can write like this one. Let us call it U1, this is V1, this is U2, this is V2. So, there are 4 displacement 1, 2, 3, 4, and accordingly the forces also we can apply a force here or not here, like that. So, that means the displacement matrix will be U1, V1, U2, V2, and similarly force also will be F1, okay, let's call it horizontal. This one is horizontal, so we will write H, FH, and like that. So, this will be FH1, FV1, FH2, FV2, right. So, forces will be here FH1, the force here FH2, the force in this direction FH, sorry, FH1, FV1s here, FV1 here, so FH2, and upward FV2. Okay. And if you look at here, if F is 4 by 1 and U is 4 by 1, K has to be 4 by 4. Yeah. So, finally, the equation, this equation we have to write Ku equal to F, and if F is 4 by 1, U is 4 by 1, K has to be 4 by 4. In contrast to the simple one which has 2 by 2 K, right, we will have, in this case we will have 4 by 4 K.